Okay, so today we'll start discussing in details the notion of a generating function, generating polynomial, generating series. So there'll be 2 lectures devoted to this topic. Today we'll cover sections 9.1 to 9.3 of the book of Grimaldi. Will be an introduction, some basic properties, and next time we'll go even more deeper and give some more examples of generating functions. But let me start by a brief reminder what we did last time. Let me share my screen. Let's see. Hopefully it will work better than last time.
Same problem as last time. Seems. Oh, now it works.
Yeah. So I did something. Hopefully we'll do not have problems today. So just a brief reminder what we did last time to keep track of things. So we were discussing root polynomials. And this is a very nice notion. So the base of this thing is that we're given some kind of funny chessboard where we take the usual chessboard, but not the standard, but the rectangular, say, with n times m squares, and then we forbid a bunch of squares, any collection, whichever we want. And then we're asking for a given number L, which is at most the minimum of n and m. Otherwise, the number would, by definition, be 0. If we're given L in between 1 and this minimum of m and n, how many rooks we can place on our board? Rook is this chess piece, such that none of them stays in the same row or in the same column on the allowed squares. So when we get, if we denote our chessboard by capital C, so we get the number R with index C and of L, where L is the number of rooks we're using. So we'll have R1 of C, R2 of C, R3 of C, and so on, up to the maximal number, which is minimum of n and m. And we arrange them in a polynomial. So we take RC of 0 is by definition equal to 1, because this is a very convenient choice. And then we take 1 plus x times R1 of R1 of C plus x squared R2 of C, and so on till x to this number, say denote this by k, maybe k of C would be x power k R C of k. So this is called the rook polynomial of a chessboard, R with index C of the variable x. So we discussed, so we associate to every chessboard a certain polynomial in one variable x. And it turns out that it has a lot of nice properties. In particular, what can we say? Some basic properties were, if we have a chessboard, which is a disjoint union of 2 other chessboards, which do not share any common rows or columns, then in this case, so if this chessboard is C1 and the other one is C2, then we have that R of C of x would be the product of those things, R of C1 of x times R of C2 of x. This is the first basic property. Then the other basic property is very nice. It says that we can calculate our polynomial kind of by induction, by going down. Namely, if we have a chessboard and if we have a chosen square here, then we have we can introduce two operations. So one was denoted by, so if this is original chessboard C, then we get C eliminated, where we just remove this square. And then we have a chessboard CS, where we cross out the row and the column. So just erasing one square is CE, and erasing the whole row and the whole column, we get this thing. And the main statement was that, what was it? RC of X. Yes, it was X CS plus CE, if I remember correctly. Sorry, R. Let me, wrong. Just 1 second. So, so we have the rook polynomial of our original chessboard C was equal to X times the rook polynomial, where we cross out the row and the column, and then to this we should add R when we eliminate just one square. Okay, finally, we were discussing connections of rook polynomials to our previous problems and to exclusion-inclusion principles, and got some examples. Okay, so yeah, I guess this is it. Maybe if I remember something else, we'll go back to that. But let's now start discussing generating functions. So new material, generating functions. So this is really very important and very basic tool, both in combinatorics and in fact in many other branches of mathematics. So as we have seen, it's sometimes very nice if we have a bunch of numbers to arrange them in a polynomial if they are finitely many. And if we have a sequence, infinite sequence of, say, real numbers, we can arrange them into a formal power series. So the basic definition would be like this: given a sequence of numbers say AK, K runs from 0 to infinity, we introduce the generating power series and generating formal power series, because I do not require anything about its convergence so far. So we have A0 plus A1x plus A2x squared plus and so on and so on. So this would be a formal expression. Okay, so in a sense, this is just another way to code a sequence of numbers, and I'm not saying anything about these numbers. In our application, the numbers would be integers often, but we can do this formal thing we can do for any sequence of real or even complex numbers, doesn't matter. So, an interesting remark, though, is that if let me call this 5x maybe. If 5x is a converging power series, has a positive radius of convergence, For example, if AK is smaller or equal than the absolute value maybe is smaller or equal than C power K for some positive C, then phi of X is a function, a well-defined function in some interval, in some, actually if you know some complex analysis, if some in some disk, the absolute value of X small or equal to number, and moreover one can differentiate phi of X as many times as you want. So as many times as we want. So it's infinitely differentiable function. We can differentiate it once, twice, and so on and so on. And the derivatives of phi can be obtained by the formal operation with the power series. We can formally differentiate the power series once and twice and three times and so on. In fact, if you know a little bit, so a converging power series represents a so-called analytic function, and analytic functions play especially important role in analysis and in analysis in complex variables and so on. These are really functions with a lot of nice properties. In particular, yeah.
Sorry, what did you write? RNAK? RNAK if P of X has a positive radius.
Positive.
What's the word that's underlined?
Remark. That's a remark.
A remark. Thank you.
So in particular, we can use Taylor formula to calculate. So in particular, if we want to calculate AK using the derivative, so you know the Taylor expansion thing. Taylor expansion implies, in particular, that AK is k factorial times the value of the k derivative of our function at the origin. Yeah. So because this can be considered as a Taylor expansion of phi at the origin, so we know by Taylor's formula that the coefficient, kth coefficients in this power series expansion equals k factorial times the value of the k derivative. Yes, so because the usual Taylor expansion says phi of X equals phi of 0, phi of 0 plus phi prime of 0x plus phi double prime of 0 divided by 2 factorial x squared plus and so on. So these things are exactly the coefficients here. Okay, so far so good, but this so far has nothing to do with combinatorics. Let's try to find some nice generating functions which would be related to combinatorics. And let me start with a very simple example. You'll soon understand why it's important for combinatorics. If we just have a sequence, so what is the generating function for the sequence of ones? 1, 1, 1, and so on. So we even have 1 at the 0th place. So this is k equals to 0, k equals to 1, k equals to 2. In other words, so our phi of x in this case would be 1 plus x squared plus x cubed plus and so on. So can you give me a different expression for this phi? A finite expression for this phi instead of the infinite series? Yeah, do you know? So
X
this,
in the to the power of k.
well, it's a geometric progression with the denominator x. So we can write it in the form 1 times 1 minus x. And this will work if the absolute value of x is smaller than 1. So this series converges to this expression 1 divided by 1 minus x as soon as the absolute value of x is 1. Yes, this is the formula for the geometric series. Yes, here the denominator of the geometric series is x, so that's you get 1 divided by 1 minus the denominator, and the denominator is x. Okay. Well, this would be our first example. We'll use it. It's not just because it's important Excel, but this function will show up very quickly in our further examples of more combinatorial nature. So what about ak equal n over k? K runs from 0 to n. So if we look at 1 plus n choose 1 x plus n choose 2 x squared plus n choose 3 x cubed plus and so on plus n choose n x power n. So this is a polynomial. So does it have a different expression? So can we rewrite it in a nicer way? Well, we definitely can. This is just, according to the binomial theorem, it's just this thing. That's 1 plus x power n. So that's exactly this expression. So we can reinterpret binomial theorem in this case that the polynomial 1 plus x power n is the generating polynomial in this case for the sequence of binomial coefficients n over k, where k runs from 0 to n. Okay, let's see. Example 3. Maybe what about that we have a finite sequence of ones? Our first example was an infinite sequence of ones. So ones at all places. But say we have our AK would be 1 if k equals 0, 1, to n, and 0 otherwise, k bigger than n. So we just have a finite sequence of ones. So our generating function in this case would be 1 plus x squared, plus say x power n. Can we write this thing in a nicer way? Here is my idea, and I'll give you a couple of minutes, try to think. So what about phi of x times 1 minus x? Can you calculate this thing? Try to calculate. I give you a couple of minutes to do that. I'll be back in 2 minutes.
Isn't that exactly the example that was in the book? So that it is 1 minus x to the power of n plus 1.
Okay. So what happens if you multiply 1 plus x squared and so on plus x power n by 1 minus x? What do we get?
Isn't that the exact example that was in the book that generates 1 minus x to the power of n plus 1?
Yes, exactly. So the answer would be 1 minus x power n plus 1, which means that our phi of x can be written in this nice closed form instead. Okay, this would be a rational function. Well, it looks like a rational function, but it's actually a polynomial, but it's a much shorter expression than the original thing. Yeah, okay. Let's see, now we have those things. And this again would be a convergent. Yeah, well, this is a polynomial, so not much to talk about. Yes, what about the following thing now? And now we'll need to use our first example. But what about if I want to do the following? Say I want to have a k equals k. K equals, I don't know, 0 can be included, 1, 2, 3, 4, and so on. What would be the generating function of positive integers? So phi of x would be, in other words, x plus 2x squared plus 3x cubed plus 4x to the 4, and so on. Can we write this in a nice way? What do you think? And the idea again here is look at the sequence which we studied already: 1 plus x squared plus x cubed plus and so on. So what can we do with this sequence? Because this we know is 1 divided by 1 minus x. How can we transform this thing into that one? Do you have an idea?
Wasn't something about derivatives?
Yeah, so if we take, yes, exactly. Let's formally differentiate this series, yes. Look at the derivative of this thing. So what do we get? We'll get 1. So this disappears. 1 disappears. So x would give us 1. Then we'll get 2x, 3x squared, 4x cubed, and so on. Yes. So it's almost what we need. To get what we need, we have to multiply it by x. So if we take x times this derivative, then it will give us exactly what we want: x plus 2x squared plus 3x to the cube plus 4x to the fourth, and so on. But derivative we can actually apply to this closed formula, because, well, in our situation, since we have analytic functions, applying derivative to the function will give us the same as applying term-wise derivation to the series. So our answer would be x times 1 divided by 1 minus x prime, which is x. Then if we differentiate this thing, we'll get minus 1, and then we get this thing squared, and finally we get another minus, I think, from inner derivative. So my guess it would be x divided by 1 minus x squared. Let me just double check. Double check. Yes. So this is our answer. Yes. So this function, this is now an actual rational function. If we expand it into Taylor series at the origin, we'll get exactly what we wanted. X plus 2x squared plus 3x cubed plus 4x to the fourth, and so on. Okay, now let me make it just a little bit more complicated. Namely, what about the sequence AK equals to k squared instead of just k? So our phi of x in this case would be x plus 4x squared plus 9x cubed plus 16x to the fourth plus 25x to the 5 plus and so on. How can we get this? Well, and the idea is more or less the same. So let's look at the letter power series. So idea, again, take the series which we had before, x plus, what was it, 2x squared plus 3x cubed plus 4x to the fourth, and so on. How can we, again, how can we transform this guy to the one which we want? The idea is the same. Let us take a derivative once again. Yes. If we take this thing, let me denote this one maybe by psi of x. So if we look at the derivative psi prime of x, so we'll have 1 plus 4x plus 9x squared plus 16x cubed plus 25x to the fourth, and so on. So again, we see that if we multiply x by psi prime of x, we're happy to see that we get exactly the phi which we wanted, namely we'll get x plus 4x squared plus 9x cubed plus 16x to the fourth plus da da da. Okay, so now our answer would be phi which we want would be equal to x times the derivative of our previous answer, x divided by 1 minus x squared here, and we have to take the derivative. Okay, what do we get? Well, we know how to differentiate, hopefully. So it's the derivative of the numerator, which is 1 times the denominator 1 minus x squared minus the numerator x times the derivative of denominator, which is 2 1 minus x, and the inner derivative gives us minus 1, so we'll have a plus here instead of minus, and then divided by the square of the denominator, which will give us 1 minus x power 4. Okay, so we can divide by 1 minus x, so what we get would be x times here 1 minus x comes from this guy, 1 power 1 minus x cancels, plus 2x and 1 minus x cubed. So I hope I haven't done any serious mistakes so far. So my answer was x1 plus x divided by 1 minus x cubed. And that's exactly what I have in my notes. You'll get my notes then later. Okay, so that's, again, this is a rational function, which if we expand it at the origin, we'll get a power series whose coefficients are k squared. And one can continue, of course. One can get k power cubed, k to the fourth, and so on, using the same trick, but the answer would be more and more complicated each time, of course. Okay, let me formulate now. So we went through a bunch of examples. We'll have some more examples soon, but let me formulate some rather general proposition, which is obvious but quite useful. Proposition: if f of x is a generating function for the sequence a, k runs from 0 to infinity, and g of x is a generating function for the sequence bk, k from 0 to infinity, from 0 to infinity, then f plus g is the generating function for the sum, of course, for ak plus bk, k from 0 to infinity. And what about the product? So this would be our first statement. Our second statement would be f of x times g of x. So what is it the generating function for? So is the generating function for what? Can you help me? If we take the product of two power series, what should we do with the sequences to get the coefficients? If we multiply two power series, what would be the coefficient in the product? The k.
The power of the highest power, I mean the powers added to one another. Like if you take x to the power of 5 times x to the power of 3, then you get x to the power of 8. So 5 plus 3 equals 8.
Okay, so for the kth coefficient, let me write the kth coefficient in the product. So we'll get a power k plus a power times b naught. Okay, a power k times b. Sorry, what is it that I'm saying? Sorry, not a power k. Okay, so the kth coefficient in the product would be ak times b naught plus ak minus 1 times b1 plus ak minus 2 b2 plus, and so on, plus a naught bk. So this would be k from 0 to infinity. Do you understand what I'm saying here? So the kth coefficient in the product would be ak times the kth coefficient in A times the zeroth coefficient in B plus k minus first in A, B1. So the sum of those indices should be k. So k plus naught is k, k minus 1 plus 1 is k, k minus 2 plus 2 is k, and so on and so on. So the formula is, well, we can write this as well as with a summation sign, but it's not so important. Summation, say j from 0 to k, a k minus j bj. So this would be the formula for the coefficients in the product of two power series, of course. That's a very simple thing. Okay. Now, the next thing we'll do now, and this is example 9.11 from the book, and we'll find the generating function for the number of choices with repetitions. So further example, which is very nice. So example 9.11. So generating function for the number of choices of n objects from k possibilities with repetitions. So we have k types of objects. So say we have, I don't know, apples, oranges, and again cucumbers, and we have unlimited supply of each of them. And we want to know, we want to pick, say, 5 objects of these 3 types of objects. So how many possible choices do we have? And I think it was lecture 2. So the answer which we formulated was in terms of binomial coefficients. And the answer, the combinatorial answer for that was binomial n plus k minus 1, choose k. And the idea was as follows. So we were introducing dividers. So k possibilities with repetitions. Yes, so we were introducing n minus 1 dividers. Yes. So this equals to n plus k minus 1 over n minus 1 also. And for this, we had the following interpretation. Say, so we have k types of objects, yes. And to choose n objects out of those k types, we were kind of introducing an artificial divider. So say we're first choosing some number of apples. We don't know how many, but when the apples are finished in our choice, we are putting an extra symbol there, an extra divisor, I don't know, putting in a book. So when apples are finished. So then the next object would be oranges, for example. We're putting a number of oranges, how many we need, but we don't want to exceed the total number of objects we have to choose, which is n. Then after the last orange, we are putting an extra book, like a divisor. Then we start cucumbers, and cucumbers, because cucumbers is our last type of object, it doesn't have, we don't have to introduce the last divisor. So the number of dividing books is n minus 1. Is yes, is n, something is, Yes, n minus 1. Okay, so so the question which I want to answer is as follows. So we'll get a sequence of numbers ak would be, in our case, n is, if n is fixed, and we want to have a generating function for the numbers. N is a fixed positive number, n plus k minus 1 over k. So what is a generating function for this number of choices with repetitions? So our series would be, so the first one would be 1. Now we get n choose 1 times x plus n plus 1 choose 2 x squared plus n plus 2 choose 3 x cubed, and so on. Okay, so we want to find a nice closed form for this function phi, which is the generating series for this sequence of numbers, whose combinatorial meaning is this the number of choices with repetitions. And my claim is, so I'm giving you the answer, but now we want to prove this answer. My answer that phi of x is actually nothing else as 1 divided by 1 minus x power n. So if we take this simple rational function again and expand it at the origin, we get exactly this power series as it says above. And how do we prove that? So the proof is as follows. So we just want to calculate what is the kth derivative of this function, of this function here. And then we will want to multiply it by k factorial and see what happens. Okay, so the kth derivative, so let me start with the first derivative. So we will be interested in calculating dk dxk of this function, and its value at x equal to 0. Okay, so let's start, say, with the first derivative. So our function is actually 1 minus x power minus n. So it's fairly easy to differentiate. There is no difficulty. So let's start with the first derivative. What about phi prime of x? Phi prime of x, if we want to differentiate this expression, we'll get minus 1 minus n 1 minus x power minus n plus 1. Yeah. If we look at what happens when x vanishes, we'll get n. And n is exactly n over 1, which is this coefficient here. This is the first coefficient in our series. Yes, also the value of our function at the origin is 1, of course. Now, what about we differentiate it twice? So we get, if we look a little bit carefully, we'll get n plus 1, and 1 minus x power minus n plus 2. So the value of the second derivative at the origin would be n times n plus 2. And if we divide it by 2, this would be exactly n plus 1 choose 2. And that's what we have here, up here. So we're happy. In general, if we look at the formula for the kth derivative of our function, we'll get n plus 1, n plus 2, da 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 da. The last one would be n plus k minus 1, and times 1 minus x power 1, power minus n plus k. And the value of the derivative at the origin would be phi k at the origin would be this product n plus 1, da 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 da, n plus k minus 1. So if we divide the value of the k derivative at the origin by k factorial, this would be exactly the binomial coefficient n plus k minus 1 over k. And that's exactly what we want. So this is the kth coefficient in the series of numbers which we are generating. So yeah, we have shown that if we have a series 1 plus n choose 1x plus n plus 1 choose 2x squared plus and so on, then this would be exactly 1 divided by 1 minus x power n, because applying derivatives, kth derivative to this conjectured answer, we get exactly the sequence of numbers we want to generate. So this is, oops. Okay, what happens now? Okay, good. This is a little bit indirect proof. I gave you the answer, but then we checked that this answer actually works. Yeah. Let's see a little bit. I think I would work a little bit with compositions. Maybe we'll start with compositions, and then I'll introduce what the composition is, and then maybe we'll make a short break after that. So, a small new section, compositions. So today we'll be discussing compositions and partitions of a given integer. These things are closely related. One is the ordered analog of the other, and they are very nice generating series for both of them. So let me start with a composition. So our definition would be as follows: given a positive integer n, its composition of length, say L, is an expression n equals m1 plus m2 plus da 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 plus ml, where each mi is again a positive integer. And that's an ordered expression. It's important that m1 is our first entry, m2 is our second entry, ml is our last entry. So let me start with a simple example. How many compositions of a number 3 do we have? So composition example, n equals to 3. So we want to decompose 3 into the ordered sum of positive integers. So what are possible compositions? Well, we have 3 equals 1 plus 1 plus 1. That's the minimal thing, yes. Then we have 3 equals 1 plus 2. So it's 1 in the first place, 2 at the second place. We're counting orders here as well. Now we have 3 equals 2 plus 1. 2 plus 1 is not the same as 1 plus 2 because these are ordered numbers. We have 2 at the first place, 1 at the second. What do we have more? And finally 3 equals 3. This is still a composition. Totally we have 4 compositions, 4 possible compositions of different lengths here. So this is length 1, we have two of length 2, and we have 1 of length 3. But now I'm just showing you all possible. What about n equals 4? So let's see how many do we get for 4. And again, I am counting all of them, all possible lengths. So the minimal would be 4 equals to 1 plus 1 plus 1 plus 1, all ones, yes. That's the longest one. Now we can have 4 equals to 1 plus 1 plus 2, yes. So we can have 4 equals to 1 plus 2 plus 1. That's a different one because the order is important. Now we have 4 equals to 2 plus 1 plus 1. So we have 4 of them. Now 4 equals to 1 plus 3. 4 equals to 3 plus 1. 4 equals to 2 plus 2. And finally 4 equals 4. How many do we get here? 8, yes. So there are 8 possible. Can you guess what about n equals 5? How many will we get?
Probably 16.
Yeah, we'll get 16 in fact, yes. So let's do this and then we'll make a short break. So how to represent 5 as the sum of positive integers, ordered sum of positive integers. We have 1 plus 1 plus 1 plus 1 plus 1, 5 ones, 3 ones, and a 2, 2 ones, a 2 and a 1, 1 plus 2 plus 1 plus 1, 2 plus 1 plus 1 plus 1, 1 plus 1 plus 3, 1 plus 3 plus 1, 3 plus 1 plus 1. Now 1 plus 2 plus 2, 2 plus 2 plus 1, 1 plus 2 plus 1 plus 2, 2 plus 3, 3 plus 2, 4 plus 1, 1 plus 4, and finally 5. So we get 16 altogether. 16 possible compositions. Okay, so let us make a break now, and so when we're back, you have to explain to me why the number of compositions. The general guess would be, of course, 2 power n minus 1. If we want to look at all possible compositions of number n, we'll get totally 2 power n minus 1. So think a little bit. If not, I'll try to convince you that this is the case. So 10 minutes break. Okay, good. Recording further. So let me explain how to get this number 2 power n minus 1 of all possible compositions of a positive integer n. And also, if we want to calculate the number of compositions with a given number of terms, say k terms, how can we get this thing? Okay, recall that the composition of a number n is its representation in the sum of terms mi, m1 plus m2 and so on plus mk, where those are positive integers and the order is important. So with m1 is the first one, m2 is the second one. We're not mixing them. So when we'll be allowed to mix them, this would be called partitions, and this would be our next topic. But let me first explain how we can calculate the number of compositions of a given number a into k summons. So here is a lemma. Yeah, so I have to share my screen. I'm sorry. Yes, hopefully it will work. Good. Okay, here is an important lemma. It's not very complicated, and I'll explain why. So the number of compositions of n with k terms, k summons, is the nth coefficient in the product in the power x divided by 1 minus x power k. Okay, why is this true? Well, so first of all, x divided by 1 minus x is the following power series. So we're skipping 1. So it's x plus x squared plus x cubed plus x to the fourth, da 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 da. It's just, it generates, in other words, AL equals 1 for L bigger or equal than 1, and A0 is 0. So x divided by 1 minus x is the generating series for the sequence 0 and all ones. Okay, now if we'll be multiplying such series, so if we take the kth power of this series, say take the q cube, for example, and we'll pick, for example, the fifth coefficient in the product. For example, this will give us exactly the number of ways to represent 5 as a sum of ordered sum of positive integers. For example, if we're picking, say if we're picking 2 from here, and then we're picking 1 from here, and then we're picking another 2 from here, this will contribute to x power 5. And this corresponds to 2 plus 1 plus 2. So if we'll, for example, we'll be picking 1 from here, 1 from here, and say 3 from here, this would be 1 plus 1 plus 3. This will give us another composition of 5, and all possible choices will give us all possible compositions of 5 in exactly three terms, if we do that. But in general, as I said, if we want to represent n as with k terms, as a composition with k terms, we have to take the kth power of this series, of this guy, and pick the nth coefficient at power x power n. This would be exactly this thing. Okay, with this lemma at hand, what can we do if we want to calculate the total number of compositions of n in some number of terms? So corollary would be that if we take the sum k from 1 to infinity, x divided by 1 minus x power k. So let me denote, I don't know, this power series as, say, capital F of x. So I'm introducing such a power series, introduce this thing, and the claim would be the nth coefficient of f of x gives the total number of compositions of n in some number of terms, in some number of terms. Why is that? Well, it's obvious. K equals 1 gives us a composition with one term. K equals 2 gives us a composition in two terms. It's according to the previous lemma. K equals 3 gives us a composition in three terms, and so on and so on. If we add up those nth coefficient from each of these series, from each of the powers, we'll get the total number of compositions of n with any number of terms. One term from the first one, two terms from the second, three from the third, and so on and so on. Okay, now what do I want to say? I want to say that now I want to rewrite this power series, and we'll get this nth coefficient of f explicitly, and it will be this power n minus first power of 2, which we conjectured from our experiments. So let us rewrite f of x. So what do we have? So f of x is actually, again, a geometric power series. It starts with x 1 minus x plus x 1 minus x squared plus x 1 minus x cubed, and so on. So this is again a geometric power series which starts with this term, and the how it's called, the denominator of the power series is again the same number. So let me factor out x 1 minus x, and then I write 1 plus x 1 minus x plus x 1 minus x squared, and so on. And I'll use the formula for the geometric power series again. So this would be 1 plus q squared plus da da da. And this is equals to 1 minus q under the assumption that q, absolute value of q, is at most 1. And so we can easily see that for small x, this would be the case, that even x divided by 1 minus x would be at most 1. Okay, so what's the outcome? The outcome would be x divided by 1 minus x. Now this series we can rewrite according to this formula: 1 divided by 1 minus x divided by 1 minus x. Okay, what happens now? So this would be x1 minus x, and here we get 1 divided by, let's see, 1 minus 2x here, and 1 minus x end up in the numerator. So 1 minus x and 1 minus x cancels out. The whole thing would be x divided by 1 minus 2x, which is, in other words, x times, here we get 1 plus 2x plus 2x squared plus 2x to the cube, and so on. So the coefficient in front of x power k would be, in other words, 2 power k minus 1. So 1 times x plus 2 times x squared plus 4 times x cubed plus 8 times x to the 4th plus. And in other words, a k equals, a n equals 2 power n minus 1. And that's exactly what we wanted to show. That the number of compositions of a given number n into all possible number of terms is 2 power n minus 1. That's what our experiments show us. Okay, now the last section for today would be partitions. So partitions, this is section 9.3 in the book. So partitions, it's also a very, very important combinatorial gadget appearing in, I don't know, thousands of mathematical papers, not just in combinatorics, but mainly in the so-called representation theory. But that's a different thing. Okay, so partitions are kind of compositions, but we do not care about the order. So a partition of n is an unordered expression n equals m1 plus m2 plus plus mk. All mi's are positive integers, and order is not important. So let's and the number, so notation, that's a standard classical notation. Pn is the number of partitions of n. So let's now look at the simplest partitions of small numbers and how many are there. So there is just one partition of 1, and this is 1 itself, so that's not so interesting. What about possible partitions of 2? There are namely 2 of them, which are 1 plus 1 and 2. So how many partitions of 3 do we have? We have 3 partitions of 3, which is 1 plus 1 plus 1, 1 plus 2, and 3. So the number of partitions grows much slower than the number of compositions. Now compositions grows exponentially. It's 2 power n minus 1, as we just proved. So this grows much slower. So I'm saying that there are 4 partitions of there should be 5 partitions of number 5, which do we have? We have 1 plus 1 plus 1 plus 1, of course. Then we have 2 1s and a 2. Then we have 1 and a 3. Then we have 2 2s. And finally, we have a 4. And now let me do the last one. What about the number of partitions of 5? I'm saying that there are 7 of them, which is 5 1s. Then we have 3 1s and a 2. Then we have 2 1s and a 3. Then we have 1 and a 4. 1 and 2 2s. A 2 and a 3. And finally 5 itself. Okay. So this is a small warm-up example. And a very important, again, gadget associated to a partition is the Yann diagram. Yann diagrams, it's more or less the same thing as partitions, but these are more kind of illustrative representation of a partition. And again, they appear in many places in mathematics. So the Yann diagram, yeah, by the way, we can always think of a partition as a composition, but with, for example, non-decreasing entries. For example, the Yann diagram associated to a partition n equals 1 plus a2 plus plus nk. So we have the condition ni and 1 bigger equal than n2, bigger equal than n3, and so on, bigger equal than nk. So it is a diagram with k rows of blocks, k rows, yeah, of lengths ny, n1, n2, and so on, nk. For example, that's a simple illustration. So what about 2, 2, 1? So 5 equals to 2 plus 2 plus 2 plus 1. And then the typical, its Yann diagram would be, so we have 3 rows, yes, 2, 2, and a 1, like this. So if we have, say, 6 equals to 3 plus 2 plus 1, then we will get the first row will have 3 squares, then we get 2 squares, then we get 1 square. So that's the corresponding Yann diagram. Sometimes they are upside down because there is this British convention or English convention and French convention. In French convention, they are bottom to top, so to say. They start from bottom. It would be 1, 2, 2 in the first case and 1, 2, 3 in the second case. But different books show them differently. But okay, so yeah, I hope you get it. Maybe I'll draw one more. Say 7 equals 4 to 1. Yeah, so we get 4 here on top, and 2, and we get 1 square at the bottom of it. Oops. Yeah. So instead of partitions, you can draw pictures like this. That's the same language. Sometimes such pictures are easier to draw and easier to understand. Okay, so our last proposition for today would be, the last statement for today would be theorem, the following result. The generating functions for PNs the generating function of the sequence Pn n runs from, I guess, 1 to infinity is the following product. It would be the infinite product, but that's the best thing we can do. K from 1 to infinity, 1 divided by 1 minus x power k. So there is no nicer formula for that. It's an infinite product, but still, if we want to calculate its, so this infinite product still has finite radius of convergence, as we'll hopefully show. And so it's a well-defined, again, analytic function. And if we want to calculate some coefficient of this infinite product, we just need to consider finitely many terms in this product, because let's see. So each of these terms is a geometric progression with a denominator x power k. So this is, for k equals to 1, maybe what I write now would be more, contain more information and will explain things easier to you. So the first one for k equals 1 is just the usual geometric progression infinite. The second one, which corresponds to k equals to 2, would be squared plus a fourth power, a sixth power, and so on. So this is k equals to 1. This is k equals to 2. So the next one would be x to the cube, x to the 6, x to the 9, plus da 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 da. This is k equals to 3. And so if we're interested in terms of, in this product of some power, say 156, so then we will be only interested in k up to 156. For larger k, we can only pick 1 in the product. Otherwise, each term except for 1, for k bigger than 156, would be definitely of power bigger than 156. So they cannot appear in our term of degree 156 for obvious reasons. So that means that if we're interested in some nth coefficient, we don't have to think that we have an infinite product. For each finite n, we are just interested in n first expressions in this product, no more. Okay, let's see. Why is this true? So let me try to show, to convince you that this is true. Now, yeah. So a partition, so we can think in the following way. A partition of n is a choice of multiplicities which I'll call mk for each positive integer k such that sum m1 times 1 plus m2 times 2 plus plus mk times k plus and so on equals our given number n. So from this it follows that only if n is fixed, only finitely many of these mk can be non-zero, and for large k, for k bigger than n, that these must be obviously be zero. So we are saying how many ones do we take in our partition, how many twos we take in our partitions, and so how many copies of k we take in our partition. So each partition is coded by this, in principle, infinite sequence, but for each n it would be only finitely many. So how many ones do we take, how many twos do we take, how many threes do we take, and so on. And now the contribution of mk times k is coded into the series 1 minus xk, which is 1 plus xk plus x power 2k plus x power 3k, picking a certain term from here. So for example, if we pick this guy, we're saying that we're taking number k 3 times. So we'll have 3 copies of k and no more. But this generating series allows us to pick 0 number of k's, which is this one, 1k, which is this term, 2k's, which is this term, and so on and so on. Now, so what do we have? The sum of Pn x power n equals. So the product of those guys, the product for k from 1 to infinity, and that's what I said, 1 plus x squared plus times, or if I wrote this product sign, sorry, let me remove the product thing. Times 1 plus x squared plus x4 plus, and so on, 1 plus x cubed plus x6 plus because so picking it, and we in this infinite product will be if we're interested in how many ways there are to get the nth power in this product. So what we pick from the first geometric progression will tell us how many ones do we get. What we pick from the second one will tell us how many twos do we get. What we pick from this guy, it will tell us how many threes do we get, and so on and so on. And this, in all possible ways, gives us exactly all possible partitions of the number n. So we can rewrite this maybe in the form the product over all integers from k from 1 to infinity, and now here we have the sum, say, over g from 1 to infinity and x power g times k. That's exactly the same expression, the shorthand for exactly the same thing I wrote earlier. Okay, so the only thing which we can probably show is that the left-hand side, this series, has a positive convergence radius, and even the right-hand side, it has a positive convergence radius. And then we get the equality of two analytic functions. So we have the equality of the formal power series, and now I want to say that these are not just the formal power series, but these are the actual analytic functions, which means that they both of them, the left-hand side and the right-hand side, has a positive convergence radius. Okay, so the left-hand side the left-hand side, which is this sum Pn x power n, has a positive convergence radius. Why is that? Well, we know that Pn, so why? Well, we have the following thing. The number of partitions is definitely smaller than the number of compositions, and the number of compositions is smaller than p power 2 power n is equal to p is equal to 2 power n minus 1. But then it means that the sum of Pn x power n is smaller than the sum of 2 power n minus 1 x power n, and this radius, this is a geometric progression, and it has a convergence radius 1/2. Convergence radius 1/2. So this series has convergence radius at least 1/2. So we are done with the left-hand side. What about the right-hand side? The right-hand side, which is a more complicated thing, is the product k from 1 to infinity, sum j from 1 to infinity, x power jk. Okay, how can we show that this has a positive? Why it has a positive convergence radius? We use a little bit of calculus here, and yeah, it's a short argument, and then I'll be done soon. So take log of this expression, take log of the right-hand side. So the log of the product would be the sum of the logs, yes. So this would be the sum. Okay, the sum of the so we get, say, the sum of k from 1 to infinity log of 1 minus 1 divided by 1 minus x power k. So log of the inverse is minus log, so we get minus sum k from 1 to infinity log of 1 minus x power k. Okay, so we want to show that this thing, why is this converging for small absolute values of x? Say for absolute value of x smaller than some constant c, smaller than 1. Okay, so let me estimate the derivative of one single term like this. And then I'll be putting this together with this, how it's called, mean value theorem for the derivative, and this will give us what we need. So one has the following estimate. So the absolute value of the derivative of log of 1 minus x power k. So first of all, this derivative equals the absolute value of minus k times x power k minus 1 divided by 1 minus x power k. This is just differentiation of log. And since we assume that x is at most, absolute value of x is at most k, we get k c power k minus 1 and divided by 1 minus c. Since we assume that c is smaller than 1, this would be correct estimate. Okay. Now, if we use this estimate in our, we look at the sum k from 1 to infinity. We are taking the series which consists of the absolute values of logarithms. So this would be a series like this. And now we'll be estimating, how should I say, we'll be using mean value theorem. So we'll be estimating the function. So since log at 1 vanishes, so this thing is at most the maximal value of its derivative times the absolute value of x. Okay? And we'll be adding up those estimates. We get sum k from 1 to infinity. K, this estimate we're getting here, k c power k minus 1, 1 minus c, and divided by the absolute value of x. And we're assuming that x itself, its absolute value is at most c. So we'll be getting smaller, again, or equal than sum k from 1 to infinity, k c power k divided by 1 minus c. And this is, c is a small number, 1 minus c cancels out. Yeah, no, sorry, 1 minus c comes out as a factor. And c, with the condition that c itself, c is in between 0 and 1, this is a converging series, and it gives us the so in this way we'll be proving that for all small k our series is absolutely converging with some explicit constant estimating it from above. And this definitely implies that the right-hand side has a positive convergence radius. And if we have two power series with positive convergence radius, which coincide as formal power series, then they coincide as functions. So the generating functions coincide. Yeah, and this would be the last thing we'll be discussing today. And I hope I haven't overloaded you too much. It's a fair amount of theoretical material. Okay, so I'm finishing now, and you still have some 20 minutes till your seminar will start.
A question before we go.
Yeah.
Yes. What's the radius in the convergence? What's the radius?
What's the exact radius? I was lazy enough. It's definitely smaller than 1, but I can probably try to figure out by next time. I'm sorry.
Okay.
I'll try to figure this out. This is definitely known, but I have to look a little bit more carefully. It's definitely bigger than 1/2, smaller than 1, but I don't know at hand. But if I'll sit maybe some 15 minutes, I'll figure this out. Okay, so good luck, and I'll send you my notes, and I'll send you also this, this thing. Okay, good.